All right, so one of the reasons I wasn't worried about talking about this topic today is that we've kind of already found some of this information. So we're going to talk about applications of all the derivatives and stuff we found in Unit 2. So how do we use all this differentiation to solve problems in the real world? And so there's no new math to learn other than how to apply the math that we already know. And velocity is actually something that we already found in our first example of calculus. So does anyone remember the scenario or how we found velocity way back on day 1 of calculus? Sounds like we're all wide awake.
First derivative?
Yeah, the first derivative, that's right. We did that on the dragster. So if you think back to the dragster, we were given a function that was describing distance. And what we needed to do was find how steep the distance curve was going, which gave us speed or velocity. And so the first derivative of distance was velocity. So if we had a function that was given as s of t, that's the displacement function. So this can get a little bit confusing with s because you think of speed. But s is also used for displacement, which is a change in distance. Okay, so the distance function is s at t. The derivative of that is v at t, velocity. So the rate of change of distance is velocity. So if you take your distance function, take the derivative, you now have a function that describes the velocity. Well, if you go and now have a function that describes velocity, you can also take the derivative of velocity. And the derivative of velocity is the rate of change of velocity. Does anyone know what that's called?
Isn't it acceleration?
That's right. Big clue in the title, acceleration. And so how velocity changes is acceleration. So if you think of you're driving and you're at a stop sign, your distance is nothing, your velocity nothing, your acceleration is nothing. As you put your foot on the gas, your distance, of course, changes. How fast your distance changes is your speed. But since you are not staying at the constant speed, you're actually speeding up. That's what we call acceleration. So the rate of change of acceleration is the derivative of velocity, which then brings this idea of a second derivative. So taking the derivative once is called the first derivative, and taking the derivative of that answer, the derivative of a derivative, is called the second derivative. So if we started with a distance function, we differentiate once, we get velocity. We differentiate again, taking the second derivative, we get another new function called acceleration. And so today we'll be doing that, just taking distance functions and differentiating a bunch of times. So we'll do this with the object and a position function. And I have a small little Desmos demonstration for you to do just to visualize this. But right now we'll do the math behind it, and then you can visualize what's going on here. So an object with a position function is given this way. So it moves along a straight line. So it might move in a certain fashion. It could be something going up and down. It could be, as I talked about, electrons in a wire. All of that could be modeled using math of something moving in a straight line. So we're just going to simply measure the velocity and acceleration of this thing. It could also be a dragster, right? Starting here, going on a straight line down the strip. You want to find out This function tells us how far we've gone. We want to know how fast we're going and what the acceleration is. So this is just a matter of differentiating a couple of times. So velocity, so v at t, is s prime at t. So we have the s function here. We now are just going to use all of our rules from last week and apply them in this question. First thing I see is a power of a function rule, which means we have something to the power of 3. So for me, I write that down like this first, bringing down the power of 3 and then taking 1 less than its degree. The inside stays the same, but then I multiply it by the inside function. So that Russian doll idea, derivative of the outside times the derivative of the inside. And then I can tidy this up just really quickly. 8 times 4, or 8 times 3 is 24. 8t plus 5 squared. So now this is a function that describes velocity. And in the question, it talks about the distance is moving in meters, and the time is in seconds, and therefore the velocity is meters per second. So if I wanted to find how far the dragster is gone, or the object, I would use this function. And if I want to know how fast the dragster is going, or object, I would use this function. But then I can go off and also find acceleration. And acceleration is the derivative of the function, or also as the second derivative of distance. And if we're doing the second derivative, you put 2 little ticks. But regardless, I'm going to take what I just found for velocity and differentiate that. And so it's just a matter of doing the power of a function rule again. I'll bring the 2 down out front, but this time it gets multiplied by the coefficient that's there, leaving the inside alone. And so the inside is 8t plus 5 times the derivative of the inside, which again, this time is 8. Tidying it up by seeing a 48 times an 8, which is 384. And this is an easy rainbow, so we could go one step further and rainbow this. But because the distance formula looks the way it does, in that it's got an 8t plus 5 in brackets, the velocity formula looks the way it does, I think I'm going to leave the acceleration formula like this. But there's nothing wrong with rainbowing one step if we wanted to. But this will make all of the formulas kind of look the same. So this guy is now the acceleration function. And the notation for acceleration is meters per second squared. Because you're taking the derivative of something that's already meters per second. It's like multiplying meters per second times meters per second. So you get this new unit called meters per second squared. And then if I want to know the acceleration at any moment in time, I would use this function. So the calculus is useful in order to be able to find all 3 of these calculations. It's also useful to help us tell us the behavior of a certain object and which direction it is moving, because of one of the things we learn about derivatives and slopes of tangents back on Unit 1. So we've got a question like this, and I'll give you a second to sort of look at it and copy it down as you need to. So this is a different scenario, different object, still moving along a straight line. This scenario could represent a particle that is starts at the bottom of something, starts down here, goes up, hits some sort of maximum point. Looks like about here, and then starts coming down, and then it looks like it's starting to go up and down, up and down, up and down, up and down. So it might be going in this fashion. Things that do this are kind of like sound waves, could be sound waves, because that looks maybe trigonometric. Could be parabola, parabolic, not sure. But regardless, we have this thing going like that. Now, it could also be up and down, or it could be moving to the right or left. And so this object could be going over here, hitting some maximum, coming back, hitting a maximum here, going like this. Could be describing something like that. It all depends on how the question is set up. So in this question, it does mention that its distance is the distance to a right of a fixed point. So that means we've got some fixed point here, and what this graph is representing is how far right the object is. So it's going off to a certain maximum and then turning around and coming back, and then going this way and this way and this way. It could also be something moving up and down, but in this one is talking about how far to the right of a fixed object it is. So when is the object moving right? So I'll ask anyone there who's willing to talk about, when do you think this object is moving right?
Whenever x is positive?
So x is along our axis here. So
whenever y is positive?
Okay, well, if we look here, could be a 0 and this could be like a 10. I would say it's always positive. So it's not what the y is positive, but I like your thinking.
Up to 3 seconds.
Okay, why?
Because that's when the distance is getting the farthest away, and then when it hits its maximum of whatever it is, the distance starts decreasing because it's coming back towards that point.
Okay, good. Now, what is Jacob talking about? Because he's right when he's talking about something being positive.
Is it the slope of the tangent?
Yes, exactly. So I know that's probably where he was heading at, in that if the slopes are positive, then you know it's going to the right. And that's an important spot. Okay, good. Thank you. So you're right in saying that it's between 0 and 3 seconds. There is another spot that it's going to the right, which seems to be after 6 seconds. So t is greater than 6. We have no evidence to suggest that it's going to start coming back down because the arrow is just going off like this. So we're going to assume it's just going to keep going off like that. Maybe it doesn't, but the arrow is just saying like that. So all I'm going to say is on that part. So it's moving to the right because the distance from 0 is getting bigger. And we said that this is distance to the right of a fixed point. So then naturally, if the distance from the right of it is decreasing, so that means it goes out here and it's getting as far away to the right. But when the graph suggests it's coming back, that means the distance from this is getting smaller, and that means it must be moving left. And so when is it moving left? Well, this part here is when it's moving left because the distance right of it is decreasing. And that would be between 3 and 6 seconds. And when is the object at rest? Well, that would be,
Mins
yeah, at the maximum, exactly.
and the minimum.
And the minimum. So at all those times, it is not moving at all, okay? And we know that because it changes from moving to the right to the left, and the slopes of the tangents, which are speed, are also 0, okay? And so it actually happens 3 times here. It happens at 0, at 3, and at 6. And what Jacob hinted at was how you can also tell this using calculus, which we'll be doing in 1 second, by looking at the derivatives. And so if the slopes of the tangents are all positive, that means the graph must be increasing, which means it's moving to the right. If the slopes of the tangents are negative, regardless of how steep they are, then the graph must be going down, which in this case means it's moving left. And if the slopes of the tangents are 0, then you know that it must be at rest. So taking all that information and doing this without a graph leads to this question. So different function. And I haven't said whether the function is moving right or left or up or down, but we have a positive direction or a negative direction. So that positive direction could mean that it's how far up it is going, or if you decide that moving to the right is positive and moving to the left is negative, okay, any of that would be acceptable. It's just a matter of when is it getting larger and when is it getting smaller, either further to the right or further up. So when we don't have a visual, it's fine. We can still find slopes of tangents to tell us whether they are positive or negative. And of course, in this case, instead of just talking about all the different spots when it's positive or negative, we're interested in 2 points, at this point and this point. What is the object doing at those 2 points? So finding the distance doesn't help us because that just tells us how far away from the center it is. So if we went back to our last example and it moved over here and we said, okay, it's 10 meters away. Well, I don't know if that right now, if I plugged it in and got 10 meters, is that 10 meters on the way up or is it 10 meters on the way back? Because our distance is just going to tell us how far it is. What I want to know is whether it's moving in the positive or negative direction. That's where I'll need the derivative. I'm going to examine the slopes of the tangents. So I'll differentiate my distance function, which is velocity. The 2/3 here for a moment looks like it's going to be difficult, but it gets multiplied by the 3. And so 2/3 times 3 is just 2. T squared. I'll do that off to the side just so you can see that 2/3 times 3, the 3's cancel and you're just left with 2. Plus the derivative of t squared is 2t, and the derivative of 5t is just 5, so minus 5. So this function now describes the slopes of the tangents, or the velocity. And so I want to investigate what the velocity is doing at these points. So at t equals 2, I'm going to sub in 2 into my velocity function. So 2t squared means 2 times 2 squared plus 2 times 2 minus 5. So 2 squared is 4 times 2 is 8 plus 4 minus 5 is 7. Now, the fact that it is a positive 7 means that it must be moving in the positive direction. You can imagine that the graph is doing something like this or something like this, and all you're noticing is that the slope of the tangent is 7, okay? So it must be moving positive. If the slope was negative, then my graph must have been doing something like this or something like that. So since velocity at 2 is greater than 0, or a fancy way of saying positive, then this object is moving in the positive direction at t equals 2. Second part of this question asks, okay, also investigate at t equals 1. So I'll give you a second to plug in 1 into the velocity function. So I got that the velocity is -1, which means the slope of the tangent is negative, which means it must be going in the opposite direction. And so since v at 1 is less than 0, which is negative, then it must be moving the negative direction at t equals 1. What would happen if I plugged in a different number and I got 0 as my answer?
It'd be at rest.
That's right. It wouldn't be moving in either the negative or the positive direction. It would be stopped. So it would either be going out to the right and then stopping and then starting to come back. So we'd be finding that spot, or going up and stopping and coming down. So again, just another application of derivatives, because we had to take the derivative to be able to do this. Now, moving things left, right, up and down, all that sort of stuff is interesting, but really, I'd be more interested in something like this. So as you're writing this down, I'll just sort of draw a picture to allow you to visualize what's going on, but we don't need the picture to solve this. So this person standing on my building, again, please don't get distracted by the awesomeness of my artwork. And we're going to assume they throw it off from this spot here. So right from the corner of the building. And they throw it off and it does something like this. So we actually answered questions like this back in grade 10 because it forms a problem. And then we found things like the vertex and all that sort of stuff because the vertex of this parabola is the highest point, which is an interesting spot. And we also found this spot as an x-intercept or a zero or a root as the spot where it hits the ground. So we're going to redo this question, but instead of using grade 10 methods, we're going to use calculus methods. Because we know what the slopes of the tangents are happening all along this parabola. So first, and this is also getting comfortable about which formula I need to use, okay, and making sure we all understanding what each formula does. So in this case, a ball is thrown upward from the roof of a building such that the description of the distance, okay, so this is the height of the ball above ground in meters, which is in meters, and given t seconds. I think that says at t seconds is what it should say. So if I want to know anything about height, I use this original function. If I want to know anything about velocity, I need to take the derivative of that function. And if I need to know anything about acceleration, I need to take the second derivative of that. So in the first question, it says, what is the height of the building? So we can calculate the height using our height function, our distance function, at the beginning, because at the beginning is when time is equal to 0. And so all we need to do is plug 0 into this function. So -5 times 0 squared plus 20 times 0 plus 25. And that's not difficult math to figure out that we're talking 25 meters per second. Or not meters per second, excuse me, meters.
Can we not just look at it as a y-intercept?
Absolutely. Yeah. Yep. You can see it right from there because it is the exact same idea as a y-intercept because x is 0, and you can see that written right at the end. But that's the math behind it. But yeah, of course. So the height of the building is 25. What is the initial velocity? So first thing I notice is I'm talking about velocity, which means I need to find the velocity function, which is the derivative of the distance function. So very quickly, I can look at our distance function and let's see here. Ryan, can you differentiate this for me?
Would it be -10t plus 20?
Perfect, thank you. So very quickly, we can differentiate this to get a new function that describes velocity. And this one's talking about the initial velocity, which is, of course, at t equals 0. So we want to find out the velocity at 0, which means we're going to plug in 0 into this formula. And we're going to get that the initial velocity must have been 20 meters per second. Graphically, what we did was we just found the slope of the tangent right at the beginning. And this here, next one, is the classic calculus question. Although all of these are classic calculus questions. But when does the ball reach its maximum height? Well, it's going to reach its maximum height right here. And we could find the vertex. But we know, if you remember back to grade 10, that was a bit of a pain to find the vertex. But in grade 12, when I know calculus, I know something special at that spot, and that is the derivative is 0. And so, when does the ball reach its maximum? It happens when we already know the velocity function is -10t plus 20. the maximum height, the velocity is going to be 0. So this idea about maximums and minimums occurring when the derivative is equal to 0 is huge. We use this, going to use this all the time in calculus. Because we know that that tangent is 0, the slope of it is 0, and that means it must be a max or a min. And so if we've got the function, we set it equal to 0, and we do a quick little solve here. So a quick little solve tells me bring the 20 over and subtract 20, divide both sides by -10. And t equals 2. So we know it's at max.
Please excuse this interruption. Mrs. Stewart, please contact the main office.
At 2 seconds. So you can see how that's much quicker than our grade 10 method of trying to find the derivative, or trying to find the vertex. So now, what is that max height? Well, again, if we found the vertex, we'd be able to find the x value would tell you where it is, and the y value would tell you how high. But we've got a function that describes how high things are going. So use c to find the maximum height. Well, what that means is take the point, or take the time of t, but now which function do I plug it into?
The original one?
Right. Remember, this green function is talking about speed. I don't want to plug 2 into the green function. I already know I'll get a 0 because the speed is 0. I want to plug it into my distance function or my height function. Okay, that one will tell us what we need. And so, but I do know it's at 2, so I'm finding s. Oh, apparently this word's gone wonky again. So we're going to plug it into the s function or the height function. So what we want is s at 2. So I'll just go up and see if I can read that again. So it's -5t squared plus 20t plus 25. So -5 times t squared, so that's 2 squared plus 25t. Is that right? Oh, no, 20t. Plus 25. All right, so that's going to be 2 squared is 4 times -5 is -20 plus 40 plus 25. So that's going to be 45 meters. So therefore, max height is 45 meters. So again, getting comfortable going back and forth between the different functions, knowing what each one tells you and what you want. And then the last part of this question asks us to find the acceleration. So acceleration at 3 seconds for this case, acceleration is the derivative of the velocity function, or the second derivative of the distance function. So let's just go up so I can see my velocity function. So there it is right there. And now I'm going to differentiate that. So quickly we see the derivative is just -10. Which means the acceleration is always -10. Doesn't matter that it's at 3 seconds or not. So therefore, it is always -10 meters per second squared. Now, for our physics people in the crowd, we should probably be looking at this and saying, something's wrong. Why is there something wrong with, not anything we did wrong in the question, not anything we did wrong with our math, but maybe something that was wrong in the original question.
The acceleration is gravity, so shouldn't it be 9.81 instead of 10?
Exactly. Thank you, Cutter. Okay, so this, whoops. Should have been, I'll say -9.8, but it is -9.81. When you throw an object off a roof, the acceleration that's acting on it is gravity. That's why, one, it's negative because it's pulling it down, and my height function was going straight up. And two, it's always the same. The math suggests it. Doesn't matter whether it's at 3 seconds or elsewhere, the acceleration, it's always slowing down at -9 meters per second. Okay, when on its way up, and then it's speeding up as it comes down, but it's always at -9.8 meters per second. Which means my question should have been back here, instead of -5, it should have read -4.9 t squared. Because when you differentiate that, you get your 9.8. Okay? So you will see many questions with this -4.9 at the beginning, because it's trying to actually replicate gravity. For simplicity, our example used -5, but we can see the problem in using that number. Now, regardless, the process that we did to answer this question is really what I'm worried about. And you can see going back and forth and getting comfortable with all three functions: the distance function or height function, the velocity function, which is the derivative of height, and the acceleration function, and knowing which one you would use in the different scenarios. So this last one is my favorite one because it makes most sense. The other ones about the moving in a straight line are not quite as obvious, but does make a bit of sense. All right, so what we're going to do now is just get a visual of what's going on here. So we're going to do a Desmos activity, but we're going to do it together. Okay, so I'll switch over to the other computer, and we'll do that part to wrap up this lesson. Okay, so I'm actually not going to release the Desmos activity yet. I'm going to just buzz through it really quickly and let you sort of play with it on your whenever you can, but it's not super important. That's why I don't want you guys to be spending all your time completing it. I want you to get the concept here. So you're just gonna watch me do most of the slides in the activity right now. And then if you wanted to go back and try it on your own, you're welcome to, or you can just watch me do it right here because it's just a visual that I'm interested in. So. All right, so here is something that's kind of mimicking what we saw in the first example, except in my first example, the object was moving to the right as opposed to up, but it's still doing the same idea. So this object, whatever it is moving in a straight line and just going up like this, and then it repeats and goes over and over. So it's describing the motion of this orange dot. Okay, if we were to draw the distance time graph here, you can see that the distance keeps increasing and then stops. So we're only interested in one cycle. So let's see if I can, sort of goes like this. So it's just a matter of how long that took. Let me see. Let's try 1001, 1002, 1003. So maybe just over 3 seconds. So I'm going to say it does this. So it's just representing the distance as time goes along the bottom. Okay, so let's see how we did. Oh, not bad. Look at that, pretty good. So now you can see the time function along the bottom. So as time goes up, the distance goes like this. So we've got this visual. Now it says draw the velocity. Well, hopefully you'll see that the speed of this is all pretty constant. So the velocity function would be all the slopes of the tangents. So if I was trying to measure the slopes of the tangents, I would go along here and say, okay, well, there's one there, one there, one there, one there. All of those are the same. And they're pretty steep, they're positive. I'm gonna say, it looks like maybe about 3 meters per second. As I said, it kind of took just over 3 seconds to get to the end. So I'm gonna guess that it's about 3 meters per second. So I'll just change this back to blue. And so I'm gonna say that the velocity is something like that because the velocity is always the same. Plus, if you think algebraically, the degree of the line is to the degree power 1. And so when you differentiate, it's gotta be 1 less, and we would end up with something like this. So I've guessed it around 3. Okay, so I was a bit high. Turns out that it's 2.5. Okay, so about 2.5 meters per second, describing that. Now, the orange point went twice as fast. What would the position time function look like? I'll let you play with that one later on, but I imagine you already know about the steeper the graph, the faster it's going. So if you wanted to play around with that, you could draw a new line describing how it will go twice as fast. And then this is one you can play around with as well. And this just goes back to even grade 9 about how the steeper the graph, the faster it's going. So to me, it looks like the red guy is the fastest, and I would say that that is A. So it's either going to be this one or this one, depending on the rest of them. Okay, so again, I'll let you play around with that. But this was the one that I wanted to really give you a chance to visualize. So you can see this object. It's almost like a bouncing ball. The only difference is a bouncing ball with every bounce gets less high, okay? So this one though, it must be in a perfect situation, maybe in a vacuum. There's no gravity happening well, there is gravity, but there's nothing holding it back. There's no dampening going on. And you can see that it goes to about the same height every single time. Let's see. Yeah, right there, every single time, okay? So describing this motion is something that we would do kind of like in our second example. So it's going up to the same height. So in this case, if I was measuring how far it went, so let's count this again, 1,001, 1,002, well, it looks like about 2 seconds. So I'm gonna guess around 2 seconds it's at its highest point, and at 4 seconds, it's back to 0, and it's starting at 0. And I'm gonna say this goes in a parabolic notion. So you guys can laugh at my parabolas, but yeah. Okay, so that's what I'm guessing it's gonna go. In a parabolic. So it kind of is going fast at the beginning, and then it slows down and then pauses and essentially 0 for a second and then goes down and speeds up. Let's see. Oh, okay, so apparently it takes longer than 4 seconds. It's saying about 6 seconds. 2, 4, 6. 1, 2, 3, 4, 5, 6. I think that's a little faster, but nonetheless. Okay, so it's got us an idea. Now, that's the position function. If we wanted to figure out the slopes of the tangent of at least 5 spots, use the tangents to draw the estimate of the velocity function. So the velocity function would be straight, right? If this is the distance, it's a parabola. The derivative of a parabola is a straight line. So if I was measuring the distances, I would see these would be, or the tangents. Sorry, let's get this bigger. So there's a tangent. Pretty steep and positive, less steep, 0. Now it goes negative and getting steeper. So if I was graphing this, I would start here. Actually, I'll start at the 0 spot. So the 0 spot, I know the derivative is 0. So I'm going to plot a point here. And I know it's going to begin up here, maybe pretty steep. I think I remember this being maybe around 7. This is just an estimate about how steep it is. And then it's getting smaller. And I know it's going to be in a straight line, so something like that. And then when I get to these ones, remember these ones are negative and getting steeper. So I'm going to guess it goes something like this. It should be in a straight line. It does say to do it in blue, so I guess I should apologize and do it in blue. So I'm going to guess it looks something like that. Let's see. Oh, look at that. Pretty bang on. Okay. Now, you should know that I knew in advance, I'd done this before, about how fast it was going. So I knew to estimate somewhere around there. And you might have estimated higher or maybe a bit lower, but it would have all gone through this spot. Okay, so whether yours was something like this or something like this, because your estimates were slightly different than mine, they all should have gone through the 0. All right, so the velocity is seen in blue. Your slopes from the previous are in red. I guess we have that. Explain why it looks this way. So we would talk about the derivatives being 1 less. And then what if we do acceleration? Well, again, this acceleration here is we're taking the derivative of this blue function. So the derivative of the blue function, if we were to do a bunch of derivatives, a bunch of slopes, is all the same. Let's get it bigger. So there's the slope, there's the slope, there's the slope, there's the slope, and all these slopes are the same, and all of them are negative. And so it asks us to draw our estimates, and I think if I estimate this right, I think it was negative 2.5, if I remember doing this right before. You could do a little rise and run if you wanted. You know, where it looks like we're at 6, and oh, it takes 3 seconds, so down 6 over 3. So I'm going to guess that the acceleration is always negative 3. Okay. So again, the derivative of a line has to be a constant, 1 less, right? And so it's a straight line. All these green slopes are the same, and I'm guessing it's negative 3 the whole time. So let's check. Oh, it was negative 2. I guess because I did 6 divided by 3 was 3, and of course 6 divided by 3 is 2. So it should have been up there. Okay. So it's just a really good visual to see all 3 of these functions happening at the same spot. The black function as a distance function, the blue function as a velocity, and then the constant acceleration function in this particular example. All right, so I will release this, but it's lowest on the priority of things to complete because we've kind of already done it. The practice on this would be much more useful. And so the practice that I've assigned, so we'll go here. I'll release the Desmos activity. If you're interested in going and playing with that, you can. But what I'm more interested in right now is releasing this. So here we are in Unit 3A. So Unit 3 I've broken up into two parts, applications of derivatives and sketching, okay? So that's why it's 3A and 3B. But what I'm going to show you here, and you should have this right now, is the lesson schedule. And if we view the material, you'll see the practice for the lesson we just did right here is page 185, number 4, 6A, 8, 9, and 11. Now, this is practice before our next lesson in Unit 3, and our next lesson isn't until tomorrow, okay, period 2 tomorrow, because our test is going to be period 1 tomorrow. All right, so when you get a chance to look at that practice, you can, but it's not a higher priority until tomorrow. Okay, so what we're going to do now is we're going to take our break. And on your way out of break, I would like you to do the first part of our review for our next unit. So you can put velocity and acceleration off to the side. There isn't going to be a question on that on our test. But what is going to be part of our test is our review. So I'm going back to, I should present this again. So on Friday, I released a review. So let's come down here. It is right here under Unit 2 differentiation, Unit 1 and 2 review. So you can get this from classwork. I think it's on our stream right here as well. So either way you get there, it gets to this, and you'll see two things. You'll see a PDF of the review, and we're going to take up all of these questions period 2 and maybe even a little bit this afternoon. We'll take up all these review questions, and we're going to start by taking up these two questions. Now these two questions you can answer right here, or you can answer in the Desmos activity. So the Desmos activity is also within this review thing. Okay, so if you click on it, you'll get access to our Desmos review. So just like in the review, there's two questions you can answer on Desmos. On the test, there's going to be two questions you can answer in Desmos. Okay, so I would like you to, the very least, try these two questions before you come back to break, and that's what the first thing is we'll review. Okay, so go over here, go to the Desmos activity, and answer the first two questions on the first two questions of the review, which are all in the Desmos activity. There's like 6 or 8 slides in the Desmos activity to do. So we'll do that with you combined with your break, and we'll come back at 10 o'clock. And by 10 o'clock, I will have hoped that everyone has completed this Desmos activity. Okay, so have a good break, and I'll see you at 10 o'clock. Good luck with the Desmos activity.
I have a question.
Yeah.
Are the questions that are on the Desmos, they're the same as what was on that PDF?
Yes,
So
exactly.
could I just do it on paper? Because I printed it out yesterday.
Yep, no problem.
Okay, great. Thank you.
Great.